Welcome to the Taming the Dragon web series. This evening I have the pleasure to have here with me Julien Enoch, which is a senior solution architect at ZettaScale and very much experience in Zenoh and anything else that came before Zenoh. Julien is going to talk tonight about how you can use Zenoh in the context of robotics application using ROS2, and in general, I would say anything that uses DDS, to address some of the limitations that DDS has when you're trying to cross the internet or perhaps trying to swarm things up. Before getting into the content of this webinar, a little bit of logistics and administrative tasks. As usual, ask questions as they come in the chat. Handout for this and previous webinar are in the handout, which are just above the chat that you have on Zenoh. I will be shortly posting, or we will be shortly posting, the links to the previous episodes, just in case you registered after the first or after the second, whatever. You will be able to see all of them. And I guess that's it. So, Julien, thank you again for being with us tonight. The floor is yours.
Thank you, Angelo. So, hello everyone, and welcome to this third episode of our webinar series about Zenoh, which will be dedicated to robotic, and more especially to robots which are using ROS2, which is a robotic operating system version 2. And we'll now see how Zenoh can help the systems to scale in various environments and also to connect to various technologies. So in the previous episode, Angelo, in the first episode of our webinar series, introduced the genesis of Zenoh and how Zenoh was designed actually according to the past experience we have in previous middleware technologies such as DDS, Corba, and a lot of technologies we work in the past for industries, defense, transport, and so on. In the last session last week, my colleague Luca Cominardi introduced Zenoh and how to get started with. You have links in this slide to all the recordings that are available online. And today, let's go with robotics and ROS2 with Zenoh. So first, a quick reminder on what is Zenoh. So Zenoh is a middleware for distributed system, and it provides publication and subscription paradigm in a push mode, like lot of other middleware, but not only. In addition to this, Zenoh provides also, for instance, the pull mode, in which as opposite to the push mode where the subscriber gets all the data pushed from the publisher to its callback. In pull mode, the subscriber can decide at which pace it will consume the data. So it will call the pull operation whenever he wants to get the latest publication data on a certain topic or a certain set of key expression in the case of Zenoh. In addition to this, Zenoh also provides a storage mechanism. So anywhere in your Zenoh system, you can declare some storages that will subscribe to a set of publications from Zenoh, and that will receive the publication and store them in some technologies. So we implement various technologies to store the data in various databases. Later on, another Zenoh application can perform some get operation to retrieve either the last publication that have been stored, either in the case of, for instance, of an InfluxDB database, to retrieve the complete time series of publications that have been made in the past for a certain set of key expressions. And with this get operation, we also have in complement the possibility in Zenoh to declare a queryable that will be able to send replies, its own replies, to a get operation. So with this get reply mechanism in Zenoh, you can build, for instance, RPC mechanism, remote procedure calls, but you can also use it to implement some MapReduce functionalities, for instance, or some voting mechanism, or a lot of different mechanisms that can be based on get and reply operation. Zenoh also works in any topologies. What we mean with this is that Zenoh supports peer-to-peer communication, either in click, where each peer is connected to each other peer, either in partial mesh topology where you have an incomplete connectivity between the peers, like on the right of the slides. But a Zenoh peer can always route data from another peer between two peers, either publication data, either get operation to go to the queryable. In addition, Zenoh supports the broker mode, so you can use a Zenoh router or even a Zenoh peer to route the data to broker the data between two clients of Zenoh application. The client Zenoh application is a lightweight Zenoh application that can connect only to one peer or one router, and it doesn't perform any routing mechanism. So the Zenoh router used as a broker can also be deployed in an interconnect way. So a set of router can be interconnected in a mesh topology, and then the router will always find the shortest path to route the publication data to the interest subscribers. And same for the queries. The router will route the queries up to the queryable wherever they are in the systems or over the internet if you deploy your routers over the internet. So now let's go with ROS2, a quick recap of ROS2. So ROS2, 8 years ago, was started when Open Robotics performed some studies to follow up with their very first implementation of the robotic operating system, and they were looking for a middleware technology to cope with more constrained environment for the robots they used. And mainly what the requirements were to be able to cope with real-time operating system with embedded devices, with really constrained environments, but also with multi-robotics and so on and so forth. So they performed a study of various middleware, including ZeroMQ, lot of different message queuing protocols, WebSockets, and DDS. And they feel that DDS was a very good fitting with the robotic system, because actually that's true. DDS has a lot of history in critical system for defense, aerospace, transportation, factories, and so on and so forth. So they, after a careful study, they choose to go with DDS as a middleware for their second version of the robotic operating system. And now ROS2 is based on DDS. So DDS is a pub/sub mechanism, is a pub/sub middleware, which is using topics to publish and subscribe. So ROS2 design made some mapping between the ROS2 concept and the DDS topic to be used. So for instance, when you do a publication and subscription on a ROS2 topic named /EBC, it will be mapped in DDS on a topic named RT/ABC, RT standing for ROS topic. A service on the other end, a service/SVC in ROS2, will be mapped on two DDS topic, one for the request, RQ/SVC request, and one for the reply, RR/SVC/reply. A ROS2 action is actually a composition of three services: one service to send the goal, one service to cancel the goal, and one service to get the result of the goal, plus two publications, one publication for the feedbacks and one publication for the status. So when you declare an action in ROS2, all those topics will be created in DDS, and you're, depending if you are the action server or the action client, you will have publication and subscription on those various topics. So far, so good. This is working very fine with DDS for ROS2. And it's working very fine actually in a wired LAN system. And why? Actually, DDS was designed ready for wired network with low message loss and high throughput and high bandwidth. DDS is actually leveraging heavily UDP multicast and UDP unicast also. UDP multicast for the default discovery protocol, that is used for each participant in a DDS system to discover each other. And then UDP unicast also to perform the discovery between all the data readers and data writers. And actually, that's also something which causes troubles in DDS. Each data writer needs to discover all the data readers it will match, and each data reader needs to discover all the data writer it matches. So you have, with DDS, a lot of discovery traffic going on at startup. So what issues can this solve? First, over the internet, for instance, at first you won't have UDP multicast. So you won't be able to leverage UDP multicast, which is a default discovery protocol in DDS, over the internet. So you need a third-party tool to mediate this discovery. In a wireless environment, you may have a lot of message losses depending the noise on radio bandwidth that is around in the environment. So what this means is that for each discovery message that is lost, DDS will retransmit the discovery message in order to establish the full connectivity, DDS connectivity between all the participants, the readers and the writers. And actually this causes sometimes troubles on discovery. For instance, recently we discussed with robotic providers that made experiments with a robot in a building on a first floor that needs to go on a second floor and taking the elevator. As soon as it goes in the elevator, the doors are closing, it loses the Wi-Fi connection. On the second floor, the doors are opening, it recovers the Wi-Fi connection. And all of a sudden, DDS needs to publish all the discovery information for all the nodes, all the readers, all the writers that are in the robot into the Wi-Fi. And this may cause some flooding of the Wi-Fi, and which takes some time to recover, and you have some time for the robot to recover the connectivity with the rest of the buildings. So DDS is very fine in wired environments, but has some troubles in wireless environment and over the internet and over generally a lot of environments where you may have a loss of messages. That's why we think that Zenoh is a good fit for DDS, and that DDS loves Zenoh actually, because Zenoh can cope where DDS has some troubles. I guess you've seen in the previous episode this matrix of feature comparison between DDS, Zenoh, and other protocol. And as you can see, actually, Zenoh will be able to cope for DDS in constrained hardware, in constrained network, and for internet-scale deployments. And how can we achieve this in Zenoh? So yes, another slide that we have it was a comparative evaluation of Zenoh and DDS made by Open Robotics a few months ago that compare. In here, you have on Zenoh on the left and DDS on the right, and you have a comparison between the discovery traffic versus the application traffic, so the real data which is useful for the robot, which is in red. So the discovery traffic in blue, you can see that for Zenoh there is a very little percentage of discovery traffic with regard to the data traffic that is required to make the robot to work. While in DDS, you will have a lot of discovery traffic occurring at the very beginning or at the recovery of connectivity that will prevent some bandwidth to be used for data publication and subscription for your robot. Same for multicast discovery. So multicast traffic in Zenoh is very lightweight because actually there will be only the discovery between the different Zenoh sessions occurring in the system, and then Zenoh has a very lightweight discovery protocol just for the subscription actually. While in DDS, of course, depending the scenario, you will have a lot of UDP multicast packets used for discovery traffic and sometimes also for data publications. So how can Zenoh help with DDS system and more specifically in our case today in a robotic system? Well, with the help of extensions that Zenoh provides with the help of plugins. Those plugins that we developed are made for Zenoh to interact with other technology. And actually, today we'll focus on this DDS plugin that is also already used by DDS user, not necessarily in robotics, but also in defense, aerospace, transportation, to bridge existing DDS system over the internet, for instance, or across different subsystems, or to bridge them to other technologies like HTTP, for instance, to have a REST API connected to DDS. But for ROS2, also these DDS plugins can help a lot the robotic systems. So what is a Zenoh plugin? Actually, a Zenoh plugin is a dynamic library. It's developed in Rust because it needs to implement two Rust traits, so a set of Rust operations, and to be built as a dynamic library, so a .so on Linux, a .dll on Windows. It's loaded by a Zenoh router, either at startup, either at runtime. With the help of the administration space of Zenoh, you can instruct a Zenoh router to dynamically load a plugin on the fly. And the good point is also that it shares with the Zenoh router, it shares a runtime. And this runtime is actually a direct access to the routing tables inside the Zenoh router. What this means is it means that Zenoh plugin can directly have a Zenoh session using this runtime, and thus directly calling operations, method call, to publish and subscribe to data directly from the router. There is no inner protocol between the plugins and the router, no serialization of data and deserialization. It's really direct call up to the network stack of the Zenoh router. And this is very efficient. But that's not all. Actually, a Zenoh plugin can also be built and statically linked to a main operation. So we do this, for instance, in the case of the Zenoh plugin for DDS. We build it as a standalone binary named Zeno Bridge DDS, which is just a main loading statically the DDS plugin and, on option, also the REST plugin for a direct REST API used on the bridge. And this Zeno Bridge DDS can be used as a Zenoh peer or a Zenoh client. So it can be deployed in all the various ways that I showed in the Euler slide, either as peer-to-peer communication between bridges, either bridge to a router and then to another bridge, for instance. So how is implemented this ROS2 plugin, this DDS plugin? In the case of ROS2, for instance, you may have a robot which is publishing some scan, some LiDAR data on a topic named /scan. So it means it will have a data writer on a DDS topic named rt/scan. And it can also subscribe to cmdvel to receive the twist command. And it means it declares a data reader on rt/cmdvel. So at startup, the Zenoh Bridge DDS will discover those writers and readers over DDS, and it will create mirroring DDS entities. So for the discovered data writer, it will create a matching data reader, so that will receive all the DDS publication. And those DDS publications will be republished on Zenoh on a key expression using the same name than the ROS topic, so rt/scan. Sorry. So when discovering a data reader, the Zenoh Bridge will create a data writer matching this data reader, and it creates also a Zenoh subscription on a key expression with the same name as the DDS topic, so rt/cmdvel. So as soon as you have a Zenoh subscriber in your system, the data will go from the data writer to the data reader in Zenoh. The bridge will republish the data on Zenoh on key expression rt/scan, and that will go to the Zenoh subscriber declared in your system. Same for a publication on Zenoh on a key expression rt/cmdvel that will go to the Zenoh subscriber in the bridge that will write the same data using the data writer that will go to the data reader in the robot. So what if I have two robots using the same topics? In DDS, of course, you will have some overlaps of topics in the same system, and that will cause troubles in the behavior of your robots. So usually what you can do is to start the Zenoh Bridge DDS and also all your ROS system using ROS localhost only equal 1 in order to have only DDS communication occurring on the loopback interface. But on your Zenoh Bridge DDS, you can also declare a scope in order to change the name of the Zenoh key expression that is used on the wire. So you will have one robot using bot1 scope, for instance, and the second robot using bot2 scope. So over Zenoh, you will have already two different key expressions that can be used. And you can have, for instance, a Zenoh subscriber that subscribes on both key expression using **/rt/can. It will receive the publication from the two robots and then can display leader information coming from the different robots. But still, it can also have a publisher only on bot2/rt/cmdvel and drive the robot bot2. And then it can also publish on bot1 to drive only the robot bot1. It can also publish on */rt/cmdvel, so the twist message will go on the two bridges and the robot will execute the twist message at the same time. So you will have a coherent movement between the two robots with such publication. The Zenoh DDS Bridge actually has two modes of discovery of behavior with regard to the discovery of readers and writers. What I just described is the default mode, also named as mirror mode, because actually the DDS Bridge creates mirror DDS entities. So it creates a writer when discovering a reader, it creates a reader when discovering a writers, and it creates those entities locally where it discovers the DDS readers and writers. Nothing goes on the wire on the Zenoh side upon such discovery. Only the declaration of the Zenoh subscriber goes on the wire. That's why actually the benefit of this is that you have a very minimal discovery traffic occurring over Zenoh, so outside your ROS system. The cons of this is that, well, as you don't have all the discovery information transmitted remotely, if you have a remote bridge also using bridging another remote ROS2 system, in this in this second system, you won't be able to perform a topic list, and you won't be able to see all the nodes graph in ROS2. Also, for services, it will work only if the server is started at first, because otherwise, if you have your ROS2 service client, which is starting at first, the bridge will discover its writer on the request topic, its reader on the reply topic, and it will create mirroring entity, and the client will think that the service is here, but it's not the service, it's just the Zenoh bridge. So the request will, the client will send a request that will go nowhere. So this first default mode is very useful when you have a kind of static ROS2 system with mainly based on publication and subscription of topics, or you may have services, but you need to have your client aware that sometimes the service might not be here because it has not been discovered yet. So you may want to start your service server side at first, or to make sure that your client can react on a timeout on a request to retry the request later on. But the Zenoh DDS Bridge also provides another mode, which is forward discovery mode. So in this mode of behavior, upon the discovery of DDS entities, the bridge doesn't create any entities locally. It just forwards the information of the discovery to the remote bridge, one remote bridge or several remote bridges. And the remote bridge will create the exact same entities, so either a DDS writer, either a DDS reader, in the remote system. So it means that, for instance, when you have a ROS2 service discovered by a bridge, this bridge will forward the information of the existence of this ROS2 service to the remote bridge that will mirror or fake this service remotely. And then the client, at startup, will discover this service and will be able to interact with. So the pros of this is that topic list will work remotely, and node graph, you will have the node graph even across the Zenoh bridges between different ROS2 systems. The cons, of course, is that you will have a little more discovery traffic between the bridges. But still, we made sure that it's less discovery traffic than in DDS. So for instance, for the ROS discovery info topic, by default, this topic in ROS publish a new version for each discovered entities. It means that if you have 100 discovery of readers and writers, you will have 100 publications of the full graph each time. And that's a lot of traffic. So the bridge will pace this traffic, sending only a few updates of the ROS discovery info over the Zenoh wire. So what are the use cases that we can perform with those bridges? The first use case, the one I just described in the previous slides, is the fleet management. You have two robots with or more robots. Each robot is running its own bridge with a different scope, and you can have a Zenoh application, which is a fleet manager, which will be able to monitor and drive the robot remotely. You can also, leveraging some storages, and more specifically the InfluxDB storage that is able to store a history of publication, you can develop a record and replay environment. So for instance, you can have a simulation robot to which you publish some twist messages. The twist messages are also received by the storage on InfluxDB, which stores this in the InfluxDB time series database. Later on, you can have a Zenoh application that just perform a get operation to retrieve the history of twist publications that have been made in the past, and will be able to republish those twist messages, for instance, to another Zenoh key expression starting with a scope reel, and be able to reproduce the movement of a simulation to a real robot. Other use cases is integration. With the help of all the set of plugins that Zenoh provide, you can have interaction from REST to ROS2, REST to DDS, MQTT to DDS, and later on, when we'll implement the Kafka plugins, for instance, we can have all your DDS and robotic publications stored into Kafka, for instance. Another very interesting use case is for microcontroller. So next week, my colleague Carlos Gimernes will introduce you Zenoh Pico. And with Zenoh Pico, you can also directly connect to a Zenoh Bridge DDS and have a microcontroller publishing and subscribing directly to a robot using DDS and ROS2. Last use case is cross-WAN bridging. So for instance, if you have two ROS2 systems in two separate subsystems, possibly with NAT, symmetrical NAT, where you cannot have direct connection between the two systems, you can leverage a Zenoh router deployed in a public host in the cloud. And having those bridges connected to the Zenoh router will be able to route all the DDS traffic between the Zenoh bridges. If by chance you can open a port in your NAT, you can also avoid this extra Zenoh router step and have establish a direct connection between the two bridges across your NATs. So just to let you know, also we are considering for next year to also implement hole punching for NAT transversal in probably we implementing the ICE and turn protocol. So times for our hands-on. So actually, what we'll do now is I will show you how to implement, how to deploy such use cases. So what I will do is that, so at first, here you have a link here on GIST where I copy and paste all the configuration files and Python scripts and HTML files that I will run in those demos. So what I will do here is in this gist, I also describe the setup. I have a Linux laptop here where I deployed a ROS2 environment with the Turtle 3 simulator. I deployed also a Zenoh Bridge DDS, and I will have also a VM running in the cloud in a website in a VM named demo.zenoh.io. And you will be able to see some feedback, so the LiDAR coming from the simulation directly on a web page served by the REST plugin. So let's go with the setup. So here on my local host on my Linux, at first, let's start the Turtlebot simulation. And let's see what we can get already with this just running the Zenoh DDS Bridge. So here, my simulation is running. I have my robot simulated here. And now I will just start the Zenoh DDS Bridge, activating actually the REST plugin directly on the bridge on port 8000. So what I can do now, in the logs, you can see that the bridge already discovered a lot of DDS topics and a lot of DDS publication, and is actually already establishing some routes between DDS world and Zenoh world. So let's see in the REST API. So here in our web browser, I can go directly to this URL. That's the admin space of the Zenoh DDS Bridge, which is @/*. And I get a lot of information about what have been discovered in the system on DDS. So I can see all the DDS participants, the writers on which topics they are running. And actually, I can filter, for instance, to get only the writers. So here I get only the discovered writers with all their set of QSs. And I can do the same with the readers. So here I have all the readers. But I can also see all the routes that have been established already by the bridges. So you can see that for each discovered topic in DDS, Zenoh Bridge is already establishing some route from DDS to Zenoh, and some route also from Zenoh to DDS. And you can see, just for this simple Turtlebot example, there are a lot. And we probably don't want to expose this all over at Zenoh systems. That's already a lot of discoveries. There are a lot of topics that are not on the purpose is not to be used remotely. So what we will do in a first step is to configure the bridge to expose only the topics we want on the wire. So let's do this with a configuration file for Zenoh. And you have this configuration file available in the gist, but I will detail it here. So first, in the declaration of the DDS plugin section for this configuration, we will declare the topics that we allow to be routed on Zenoh, and only those topics will be routed over Zenoh. The CMDVEL, to be able to remotely drive the robot, the scan to get the LiDAR information remotely, and the battery state also to supervise the battery when we'll have a real robot. In addition of this, I also here configured the maximum frequency of retransmission over Zenoh. What it means? It means that the Zenoh Bridge, by default, ROS2 topics publish the information as a certain rate, which is usually quite high. It might be 10 Hertz or more. And for battery state, for instance, there is no point really to get 10 updates of the battery percentage per second. So what I do is I downsample all the publication over Zenoh at only 0.2 Hertz. Same for the LiDAR information. as the leader information in this example will be shown in a web browser, all the leader information will go over HTTP, and it's probably not a good idea to have high frequency HTTP publication over the wire. So we'll downsample the frequency of LiDAR to only 5 Hz. Here, I will also use a scope, so the scope Simu for my simulation robot. And those two options, generalized subs and generalized pub, are actually optimization for the Zenoh discovery. What they mean is that when declaring a subscriber on /simu/something, actually Zenoh will only publish one discovery message. It just publish a message saying, I'm declaring subscription to simu/anything following this simu prefix. And there is no other point to send other discovery messages for each topic. Only one message will be sent. And same for the publications. So in addition, here I can activate the REST plugin, and I can also configure my DDS bridge to connect to a Zenoh router that I will start remotely. So that's this Zenoh router here, which is running remotely, and that I will start right now. So now, let's start. At first, we can start this bridge with the configuration. So here, I'm starting the bridge with the configuration here. And I can already directly see the difference in the route in the admin space. So here now, I have only the routes that are allowed by my configuration. The scan route, the CMDVEL, and the battery state is not here because the simulation doesn't publish any battery state. And now I will start the Zenoh D, so the router for the Zenoh router. I just start the plain Zenoh router, which by default starts also the REST plugin. And now, if I do the same request, for instance, on demo.zenoh.io, and I will scope only to the simu, I get the exact same route, but remotely. So in the GIST, I also copy and paste here a HTML page, which is actually this web page that you can see here, and that I will load here. So you can see here already we have the LiDAR information coming from the simulation to the web page, going through the router deployed in the cloud. And I will just show you quickly how this page is done. So interesting part of this web page, at the first you have all the declaration of the HTML tags, but we have also the script part, so it's JavaScript. And in this JavaScript part, we declare all the data types that are published by ROS2, and with encoder and decoder functions for the CDR encoding type, which is encoding used by DDS. So we just redeclared all the types which are used for this web page. So we have quaternions, we have the twist here. So that's how we publish twist from the web page. And we have, for instance, the battery state, and that's how we get the battery state subscribed in the web page. And here is the LiDAR scan. And the interesting part is here, for instance, here you have the function to publish twist message. So those twist messages are constructed here. And actually publishing a twist message to the REST API is just sending an HTTP request with the body as a twist message. And this will be republished over Zenoh and then republished over DDS by the Zenoh DDS Bridge. And for the subscription, for instance, here we have a subscription to ROS out topic. Well, it's just an event source, so HTML5 event source that is declared here. And we have this callback function that will receive the data from REST API as a JSON, extracting the payload, which is really the CDR encoded data in the JavaScript here, and will decode this buffer as a log object that we can then display on the web page. So now let's see how we can drive this. So here from the web page, I get the LiDAR view. I have here the possibility to publish some twists, and when I click on the button, I have some twist message published and going up to the robot in the cloud. So now, next step is that we'll add a real robot with a camera. So actually, we have here just nearby a similar robot to this one, a real turtlebot with a USB camera plugged in this robot. And it's running already Zeno DDS Bridge, but using the bot1 scope. And it's also running a Z-capture application. You have in the GIST README description, you have the links to the GitHub repository where you can see the code of this Z-capture, and you can also build it directly on your robot if you want. So this Z-capture Zeno application is also publishing each frame, so each camera frame directly on a Zeno key expression named bot1/cam/0. And in the Zeno router, I will add a web server plugin, which is slightly different of the REST plugin. The REST plugin is actually serving data wrapped into a JSON format. Like all the REST API, you have a wrapper, a JSON wrapper around the real data. And that's not very convenient for a web browser, for instance, that need to extract the JPEG image from a JSON and then to display it. So with the web server plugin, actually, that's really the real image, not wrapped into JSON, which is made available to the web page as a motion JPEG. So here in the web page, you can see in the index, you will see that the display of the camera here is only motion JPEG. Get back directly from the web server plugin. So it's already running. So in this web page, I will now change the subscription here to be bot1. By setting the subscription here. And okay, we just miss the camera. I will try here. Loading the page. So it seems we lose. Oh no, I know. I forgot to restart the bridge because, yeah, the Zeno router, which was started here, was not running the plugin, the web server plugin. So that's exactly the purpose of this Zeno D config file, which is available in the GIST, where it's just for the router configuring it to start the REST plugin and also the web server plugin. So now I'm using this configuration file. And here, if I reload the page, yeah, I have the camera available here from my robot. So here I'm changing also the key expression to be published by the robot here, by the web page here. And now I can twist the robot, and you can see me here in the robot camera. So you can see also the LiDAR coming from the robot. So there is a big pack here in front of the robot. You can see also here the door open, which is the door of our office. So we are in the corridor here. And you can see this is really reactive view from direct view from the robot. So now, what if publishing twist message? I'm publishing star, so meaning it will match the two robots, the real one and the turtle one. Well, actually, the two robots are now moving. So far, so good. So now let's go to the last demonstration, which is integration with MQTT. So we also developed a Xeno plugin for MQTT actually. And this is also available as a standalone Zeno Bridge MQTT. So in this Raspberry Pi here, I have a CON-B USB key, so a ZigBee receptor key. And this Raspberry Pi is also running here. I will show in the slide. It's also running the ZigBee to MQTT software, which is widely used in IoT. You maybe have one running at home if you use a Home Assistant, for instance. And we have a ZigBee button here, which is registered to this ZigBee to MQTT. And each time I click, it will publish to MQTT. The MQTT message will go to the bridge MQTT because this bridge actually acts as a MQTT broker. There is no need to deploy Mosquito or whatever MQTT broker here. The Zeno Bridge MQTT is the MQTT broker that you need. And this bridge will also republish all the MQTT information to a Zeno key expression named ZigBee to MQTT /device /button. And this will go to demo to Zeno.io. And also in the gist, you will see there is a Python script, which is a Python script here that I will run on my laptop. So this Python script is also establishing a Zeno session connected to demo.zeno.io, so the router in the cloud. It will subscribe on Zeno to this button, to this key expression. That's a key expression for the ZigBee publication for the button. And for each publication, it will send some twist on the simulator for the simulated robot on simu/rt/cmdvel. So here we have the Python code to publish the twist message being declared here on the top of the Python script with the CDR encoder and decoder functions. And here we have the callback for the Zeno subscription on the message which are coming from MQTT. So what we do is for each received sample, we decode it as JSON because ZigBee to MQTT is publishing JSON messages. We check if the action is a single push button or a double push button, and depending on this, we spin on to the left or we spin to the right. And then we just need to declare the subscriber with the button callback and have a loop waiting for everything. You see this simple script, 65 line of code allow to perform the bridging between a publication in JSON made by MQTT to a publication in a CDR format for DDS. So let's run this script. And now if I push the button, you can see here the log of the reception of the sample. It's a single push. The script is publishing one twist to spin on the left and then one twist to stop. And if I click twice, it's spinning in the other way for 2 seconds. So you can see now how easy it is to interoperate your robot with MQTT or with HTTP or with whatever other technology we will or you will be able to plug onto Zeno. So what did we learn today in this webinar series? Well, first, it's quite easy with Zeno to interoperate DDS system and ROS2 system with other technologies and to have this scaling at internet level, leveraging a Zeno router somewhere in the cloud. Actually, one or more several Zeno router, because for fault tolerance mechanisms, for instance, you can deploy several Zeno router in different public VM instance in the cloud, having your bridge connected to each, and Zeno will automatically do the failover if ever one of your VM is failing. So what's next in the future for Zenoh in a roadmap? Actually, we know that ROS1 is also lacking some such feature of interoperability with other technologies and also scalability over the internet or over wireless system. So we already started actually to work on a ROS1 bridge for Zenoh. And we'll also in the next future make also evolve this ROS2 bridge in order to be able to interoperate with this ROS1 bridge. So you will also be able to use Zenoh as a bridge between ROS1 world, ROS2 world, and other technologies world. So thank you for your attention. That was my my last slide. So don't forget to visit our website. You can see the code and usage of the more details on usage and configuration for the Zenoh DDS plugin on the GitHub website for this. And if you have more questions, of course, ask your question in the chat right now. I will be able to answer right now. We have a few 10 minutes left for questions. Otherwise, if you have questions in the future, just join our Discord server. Thank you for your attention. And if you have any question, shout now. So, yes, I see. Thank you, Angelo. I have some questions. So can you show an example of how to interact ROS2 via Python? So that's actually exactly the purpose of the Python script I showed bridging the MQTT publication to Zenoh. So you can see already here or in this script how you can interact in Python with ROS2. So for instance, yeah. In this Python script, it's a pure Zenoh application where you have a Zenoh configuration. You open a Zenoh session. All that you need actually is to just declare the ROS2 message in Python format using PyCDR to declare the encoding of your Python type corresponding to the ROS2 types into CDR to be published on DDS. And you just construct those objects, serialize those objects, and calling put to publish over Zenoh, and then those samples being bridged to DDS. Similar for the subscription. For the subscription, you receive a sample with a payload. So here it's a JSON, but in case of DDS subscription, you will get directly a CDR format that you can deserialize into a Python type, and you will be able to see your Python type. So actually, we have also other example. If you search on the web, for instance, GitHub Zenoh demos, you will have here this repository. So github.com/eclipse-zenoh/zeno-demos. And in this repository, there is a ROS2 directory in where you have different examples of ROS2 usage with Zenoh, Zenoh Python, Zenoh Pico, Zenoh Rust, and Zenoh using the REST API. So next question. Could ROS2 services be mapped to Zenoh queries? What will be the benefit? Actually, that's something we consider for a future version of a bridge for ROS2. It's not made right now by the Zenoh bridge for DDS, because actually this bridge only bridges the DDS publication and subscription. There is no specific code for recognizing a ROS2 service mapped on DDS publication and subscription. So we consider to do this in the future, because the benefit actually will be really that you've seen, for instance, the service is a set of 2 topics with a Zenoh query and queryable, it will be only one declaration of discovery. And same for action, for instance. We can map an action directly onto one or two, three actually Zenoh queryables, and it will benefit all the discovery traffic. And also, it will benefit also in the future the mechanism of retransmission of queries and sequence number in the queries that Zenoh implements natively. So where you use forwarding discovery for today's demos. So in today's demos, well, in these demos, I didn't show the forward discovery. We are not using this, but we already experiment those in the past. So for instance, I made the same testing with a Turtlebot simulation and Turtlebot, real Turtlebot, and then seeing the ROS graph across different two systems using ROS RQT to see all the node graph. Next question, so how about microcontrollers? How can I use Zenoh to integrate microcontrollers with ROS2 instead of micro-ROS, since I think that Zenoh API is easier to use and overall far more efficient? That's a very good idea, and actually that will be the goal of the next episode, episode 4 next week, where my colleague Carlos Guimarães will explain everything about Zenoh Pico and how Zenoh Pico can be deployed on microcontrollers, something as small as a ST32 or Zephyr or Arduino. And he will also demonstrate how this can be used to publish and subscribe directly to ROS2 with the intermediate of the Zenoh to DDS Bridge. Next question, can I use this for regular DDS application? Yes, actually the Zenoh Bridge DDS was made ready for DDS application. It really maps DDS publication and subscription as Zenoh publication and subscriptions. Yeah. So that was the last question so far. So if you have any other questions, we still have a few minutes left. Otherwise, I think we're good. And anyway, if you have further questions, don't hesitate to join the Discord. You can publish your question either in Z support or Z development channels. Thank you very much for your attention. The recording of this video will be available soon on Demio. And thank you and see you soon. Goodbye.